1 ounce of force from an imbalance in sunlight can steer asteroids into Earth-crossing orbits and drastically alter the layout of the solar system. Would you believe that sunlight has the ability to change the course of asteroids and comets? It can. Consider the example of asteroid 1999 RQ-36. On May 19, 2012, at the Asteroids, Comets, and Meteors 2012 meeting in Japan, astronomer Stephen Chesley presented the most accurate determination of the asteroid's orbit to date. The accuracy, akin to knowing the distance between New York and Los Angeles to within 2 inches, reveals the delicate nudge of the Yarkovsky effect, the minuscule push imparted on the asteroid by nothing more than sunlight. RQ-36 is under intense scrutiny as the target of the Future Origins, Spectral Interpretation, Resource Identification, Security, Regolith Explorer OSIRIS-REx. This mission will rendezvous with the asteroid in 2019 and then return a sample to Earth. To ensure that the intrepid space probe can find its way to its target, scientists have been monitoring the asteroid's orbit since its discovery in 1999. With every close passage, radio telescopes bounce signals off the asteroid's surface. By measuring the delay in the return signal, researchers can accurately measure how far the asteroid is from Earth. Repeated observations in 1999, 2005, and 2011, using the Arecibo and Goldstone radio telescopes, refined the 30 million kilometers closest approach distance to an accuracy of about 300 meters. Knowing the precise orbit of the asteroid is essential to a successful spacecraft encounter. But it's also a fantastic test of the little-known Yarkovsky effect. Light exerts pressure on anything it strikes. The amount is phenomenally small. But if exerted consistently over many years, it adds up. What's more, the shorter the light's wavelength, the more energy it has, and the more pressure it can exert. Afternoon on an asteroid, much like Earth, is warmer than wherever it is morning. And, of course, the daytime side is warmer than the night. A warmer surface radiates more heat into space. More heat means more energy, and more energy means more pressure. And for every action, there is an equal and opposite reaction. The infrared light carrying heat into space imparts a slight pushback on the surface. With most of the energy coming from the afternoon and early evening regions, that leaves a slight imbalance in this radiation pressure. The asteroid feels a gentle thrust in the direction opposite where the sun sets. For prograde rotators, or asteroids which rotate in the same direction they are orbiting, the asteroid gets a push in the direction of its orbital motion. The asteroid speeds up and moves out to a slightly larger orbit. The opposite happens for an asteroid rotating in the opposite sense from its orbital motion. Such a retrograde rotator gets pushed backwards. It is effectively slowed down and falls towards the Sun on an increasingly smaller orbit. The effect was first described by a Russian civil engineer named Ivan Yarkovsky around the year 1900. Yarkovsky, born in 1844, worked for the Alexandrovsk Railway Company for more than 20 years. Exploring railroad technology. During that time, he also dabbled in other scientific pursuits. His interest in the motions of the planets led to the publishing of a pamphlet describing the effect that would come to bear his name. His work would have been lost had it not been rediscovered by Ernst Hoppe and made widely known in 1951. Asteroid RQ-36 is one of several for which this effect has actually been observed. After 12 years of observations, RQ-36 has wandered by about 160 kilometers from where it should be. The discrepancy is entirely the result of heat radiating from the asteroid's surface. Like the proverbial tortoise racing the hare, slow and steady is the way the Yarkovsky effect manifests itself. If you guessed that the thrust imparted by radiation is tiny, you would be right. The 68 million ton, 1/3 mile wide, asteroid is being pushed around by a force equal to, as team member Stephen Chesley put it, the weight of 3 grapes on Earth. That's just half an ounce. Understanding the evolution of our solar system requires taking into account all the forces at play, no matter how small. If the weight of 3 grapes can shove an entire asteroid off course by 100 miles over just a dozen years, what about over 1,000 years? Or 100,000? Or a billion? In the 112 years since Yarkovsky published his musings, planetary astronomers have come to realize that his effect has most likely dramatically changed entire families of asteroids and played an essential role in the movement of objects from the main asteroid belt to Earth. In fact, absent this effect, the Earth would have experienced fewer asteroid impacts over its history. One is left to wonder if any mass extinction were the result of just half an ounce of pressure on one side of a rock quietly orbiting between Mars and Jupiter. Astronomy often focuses on the large, the vast, and the highly energetic. But sometimes, very small forces can alter the evolution of an entire planetary system. The Yarkovsky effect is one example. An imbalance in the radiation of heat off an asteroid changes its orbit. And that can make the difference between the status quo and mass extinction.